All right, let's now go over some important information. Okay, so your assignment number 2 will be due, I believe, on Wednesday midnight. So do the best you can, and then I'll give you the solution on Thursday. So you can take a look. And then on Friday, the tutorial session this Friday, we're going to go over the assignment number 2 solution together, some highlights. Okay, and then your test number 2 will be next Monday, November 24th, right? That's something we've been talking about. And you should have already received some e-class announcement from me today. So if you are interested, same deal as the midterm course evaluation. So this one here will be the official one. So if you're interested in participating, just say something about how you feel about your learning experience for the course. Say anything you like. I will not be able to see any result until January 15th, I believe. It's way beyond when I have to submit the final grade. So you can definitely feel free to say whatever you like in the course evaluation, okay? So, and I'll give you guys some gentle reminder just to, for the early participation, it will have to be Thursday, 10 p.m., I believe, right? Just take advantage of the early participation window. Any questions in general? I'm going to talk about the coverage of your test number 2 as well today. I'm going to make the PDF guide, hopefully tomorrow, but I can talk about things already, so you can definitely get some idea, okay? All right, let's talk about very quickly test number 2. Okay, it will be very similar to your test number 1. So your test number 2, Williams Small Center 106, okay, and then 4:30 to 5:20, the same. Okay, it's going to be next Monday, November 24th. The coverage, only the graph lecture, starting from 33 all the way to 72. Okay, I'll show you very quickly about what it is. Oh, actually, there's something I forgot to mention as well. I'll get there. Okay. It should be graph lecture plus one thing as well. Okay. So 33 is just about where we start talking about the edge list graph. I think that one there you should also review because the programming part for assignment number 2 is also about the edge list. Okay. So it should really start from right here. Okay. So slide number 33. Okay, so this is the starting point, just to review the programming part for 33, and all the way to 72. Okay, so, okay, let you know. Okay, 72 is about the comparison of all the 3 strategies for implementing the graph. Okay, so that's the range. Plus, we also need to talk about, okay, I forgot to list. Okay, that's my bad. Okay, I'll put it right here. I also put up some new slides just earlier this morning. There's also the lecture, which I'm going to do today for sure, on priority queue and also heap. Because in order for us to really understand thoroughly about how we can derive the efficient running time for Dijkstra algorithm, we have to actually review priority queue, especially how you can implement it using a heap. So we're going to do some review for sure today. That's my plan for today. All right. So there's slides there. You can also see them on the lecture side. I'll show you. You can see them right here. Lecture 5, priority queue and heap. Okay, that's something we'll do today. Okay. And also assignment number 2, right, which you're doing right now. Okay, the paper part and also the programming part. So the format for your test will be similar like last time. You got to import some starter projects and also past test cases. So there are 2 kinds of questions you may want to get prepared. So one of them is to implement some graph operation. It's a method just from scratch. For example, how do you actually compute incident edges, for example? Incident edges. So this one here is something I briefly mentioned last Wednesday. You might be given some working version of DFS or BFS. For these 2, you may want to refer to the reference solution that I'm going to release. Of course, the solution there is just my way of solving them, but they are completely consistent with how we trace the BFS and DFS in class. So it's not really bizarre for you to study them. So study these 2 very carefully, and then you might be asked certain graph operation which will have to call these 2 as a helper method. So you don't really have to develop DFS or BFS from scratch. All right? So you can think about for your assignment number 2, how you calculate the number of connected components is one possible question. Right? I'll try to give you some reasonable one that can be solved. Right? I haven't really finalized the question yet, but these are the 2 possible kinds of programming questions I can give to you. Okay? So either this or this. And of course, that's something I'll put in the guide as well. You have to get yourself familiar with about the hash map and also hash set and also array list. I think that these should be sufficient. So these are the ones I kind of use in my solution, okay? And like last time, you will be given access to the API page. So you don't really have to memorize all the method name, but get yourself familiar. So if you have to refer to them, it can be quick. So API page will be available during the test. Okay, I'll put it here. So Java API page will be accessible during the test. Okay. And the written part for the test will be also like last time. There will be some multiple choice questions, and there might be some written questions as well. Short answer, justification, and also maybe some little proof. It could be possible. But if you study the slides, iPad notes, any example we went through, and also the solution for assignment number 2, you should be fine. Okay. Questions about test 2? I'm going to release the PDF guide for this one here either tomorrow, definitely before Wednesday's class, but there should be no surprise to you. Okay? But definitely anything I put on the PDF guide will be the finalized version. Okay? Yeah, just remember when you study for the slides, make sure you do the graph one and also the priority queue and heap, which we're going to do today. Okay? Okay, so one more thing I want to mention. So for Wednesday's class, okay? So for today, I want to finish, hopefully I can finish the whole thing about heap and also priority queue. After that, I still definitely want to go ahead and derive the running time for Dijkstra algorithm, and also I want to cover the final implementation strategy for graph, which is called adjacency matrix, and then compare all the strategies together. Okay? So for Wednesday's class, I would say approximately, maybe in the first 40 to 50 minutes, I think we might still do the normal lecture. Okay? Okay, so these stuff, which I want to make sure I finish everything that's going to be covered on your test number 2. Okay, and then hopefully for the remaining part, about up to maybe 30 minutes, we can do maybe some Q&A. But in the worst case, if I'm not able to really leave any time for Q&A here, I will maybe give some extra office hour, maybe over Zoom, maybe definitely before Monday, so you can still ask me questions. You know, it's a workaround. Okay. Or Zoom, office hour. Well, potentially I can make myself available earlier, maybe on Friday, since you will be on campus anyway for the tutorial, so you can also come. Okay, so we'll see. Okay. Anyway, I'll definitely make some time for you, so you can ask me questions. Okay, guys, any questions? All good? Okay. So let's do a quick recap from last time. Okay, and then we're going to go ahead. Oh, actually, so also for the tutorial that we did last Friday, you can also find them right here. Okay, week number 10 about looping variance is definitely something you want to study as well, right? About looping variance. Okay. Okay. So let's look at the lecture from last Wednesday very quickly, and then I want to show you one fragment of the Dijkstra algorithm. And then I want to get onto priority queue and heap for today. Okay. So we talk about, so if you want to somehow show the correctness of loops, you basically got several things. You got precondition, you got postcondition. Normally, you should really try to derive these two. Precondition is just about the condition on the input. Postcondition is about the relation between the input and the output. That's something we said quite thoroughly on Friday. And then for the loop itself, you want to basically derive something called looping variance. Invariant in the sense that the condition should always remain true. Under no circumstances should it become false. Otherwise, you got some violation for the looping variance. You want to show that the looping variance will be established right before the very first iteration, and also looping variance will be maintained between between subsequent iterations. Right? So these are the two things. And you can also revisit the flowchart. Oh, I still got to fix that, right? I'll do that. Okay. And then we definitely gave some example about certain looping variant and do the tracing table. We did it again in the tutorial example also on Friday. You may also want to revisit that example again. I think that one is going to be more complicated than this one to understand how things might fail if you're given somehow the wrong loop invariance, may not be exactly wrong, just on the edge cases, it's not exactly right. All right, so some exercises for you guys to try. And then visualization about everything together. You can also refer to them. Ultimately, we want to somehow show that when we exit from the loop, meaning that the while condition there is actually false, right? And then the loop invariant has been maintained throughout, even after the last iteration. And then we want to say everything here should entail the post condition. That's how we argue about the correctness of the iterative algorithm. And then this one here is more about, the Dijkstra shortest path algorithm, right? So you can revisit about the loop invariant right here. And we try to specify that logically, either by version number 1 or version number 2. Specifically, we create some imaginary set called capital S. Think about S is going to be the set of vertices that we have finalized so far. Finalized means they have been already removed from the priority queue. All right. So here, the capital S set is going to keep growing until you can cover all the vertices, in which case the priority queue will be empty. In that case, we terminate the iterative algorithm for calculating the shortest path. Okay. Also, you got to revisit this loop invariant as well. And we spoke about the Dijkstra algorithm. Its correctness really depends on some fundamental assumption, meaning that we have a weighted graph, but every weight value, numerical value, must be non-negative. If you got negative value, for example, right here, it is possible that you may actually calculate the wrong value for the shortest path, right? You can also revisit this example here to see how that might happen, okay? Also something we traced very carefully last Wednesday. All right, any question from last Wednesday? Yes?
Scanning the elements from the queue part. Like I remember when we were covering it last time, there's like the two main conditions. There's like the main thing.
Oh, you mean the vertex must be in the queue?
Yeah. Like
oh, you talk. Okay, good. Yeah.
That you said worked for...
Yeah, I know what you mean. Yes, I actually found that place. It was actually indeed on the slides. That's something you will see. Again, I'll tell you what you should know for that detail for this course. Okay, I'll show you guys. Give me one moment. So Josh's question is, what if we try to relax that assumption about the V should be in the capital Q, right? It's about, oh, by the way, so on slide number 66, when we try to analyze the running time, which we'll do either a little bit later today or maybe in the beginning of Wednesday. So this is just another way to present the Dijkstra algorithm. Before, we were just trying to get some intuition and also try to trace. We don't necessarily have to go over this algorithm. But now, since we understand the algorithm much better, we're going to look at this more like a pseudocode version. And then we're going to look at the running time, either today, later, or maybe Wednesday. Okay, so back to Josh's question, right here. Okay, so when you look at the looping variance slide number 65, you will see there is one bullet point right here, okay? So this one here is saying, if somehow you want to really calculate the shortest path given a weighted graph where you must have some negative weights, which is possible maybe for your particular application. In this case, number one, you should not choose Dijkstra, because the way Dijkstra works is you should only look at the non-finalized, which means the vertices not that's still in the priority queue. However, if you want to relax this assumption, it is possible. So one possible algorithm is called the Bellman-Ford shortest path algorithm, but you only need to know the name for this course. We are not going to cover this. But the way it works will be kind of similar to Dijkstra, but there are certain places you have to somehow relax, okay? But just for your information, it turns out this one here, the running time is going to be worse than the actual Dijkstra algorithm. You have to pay some price. But we haven't even derived the Dijkstra algorithm just yet. But we'll do that, again, either today or Wednesday. So when you study just for this particular point, what should you really know? You should just know that just by using the standard Dijkstra algorithm purely, you cannot really handle any negative weights. You might just run into incorrect answer. But what if you really want to handle negative weights? In that way, you have to use something not Dijkstra, maybe based on Dijkstra. And this one here is just one example, the Bellman-Ford. Okay, so here, oh, sorry. Did I miss my cursor. But anyway, so the Bellman form that you can see on the slides. All right. And then something very quick, and then we'll get on to Dijkstra priority queue. So these are the tutorial example we did. And then let's see, I want to just go to one very quick reference from before, and then we'll get from there, go from there. Let's look at the Dijkstra algorithm very quickly. I want to refer to a particular line or lines right here. Right here. Okay. So first of all, we talk about the queue that we're talking about. It's not a first in, first out queue. It's something called priority queue. You may have already seen that maybe in 2101, but maybe a while ago. But let's now learn this again. Right? We're going to learn about what priority queue really is. And then what are the operations we are performing on the priority queue in the Dijkstra algorithm. Number one, we want to find out what's the minimum. And then we may actually want to insert some vertex into the priority queue. We may want to remove something from the priority queue. And very importantly, whenever you're updating the D value for the particular vertex, you may have to update a heap as well. So all these operations will come with some running time that you have to know. And to really know them, you have to revisit. We have to revisit heap again. That's why we're going to cover them today. All right. So these are the operations. Let's cover all these for the heap today, and then when we get back to the running time for Dijkstra, it will make much more sense. Okay, we'll get there. So let's now talk about priority queue. Okay. So let's now start with a new mini lecture on priority queue. Just enough for you to understand. Sorry, there we go. Okay, so let's start with the priority queue. Let me just get my notes here. And the lecture slides will be here. We can go over some bullet point very quickly. Right here. Okay. So priority queue. So priority queue is an ADT. So there's certain standard operations that we have to support for priority queue. So we will see what they are. And also, we are only looking at how you can implement a priority queue efficiently using a heap data structure. Beyond the lecture, you may want to also do some important exercise to think about what if you don't really implement a heap to support the priority queue operation? What if you use an array? And what if you use a singly linked list? And what if you use a doubly linked list? Think about that direction there. Okay, that's something we can assume you know at this level. Okay, that's something you may want to think about. And then also we're going to look at time complexity, right, about a heap. Okay, so let's start with what's really a priority queue. It's a collection, and then it's a collection of entries. Every entry is actually an element and key pair. Okay, so let's pause here and then build up something. Okay, so this is conceptually a priority queue, right? Of course, behind the scene, you can think about this more like a public perception about what a priority queue is. But when you want to support this kind of an efficient operation for priority queue, you may want to use some nonlinear data structure like a heap. That's something we'll see. Okay, so let's start with here. So for our context over here, so when we talk about priority queue, specifically we talk about minimum key priority queue. Minimum key priority queue. So what that means is the lower the key value, the higher the priority. Let's draw some connection right away. Okay? In our Dijkstra algorithm, the capital D value is the key. In that case, the lower the capital D value, the earlier we should really choose that particular vertex from the priority queue, right? That's exactly here, right? So you can think about key value here. For example, it could be the capital D value for some vertex. In which case, priority, that means the minimum DV chosen first. Okay. Good. And if you look at individual entry, we got key element, key element, key element, and etc. Okay. So for example, in this particular case, we can identify the lowest key is right here. Okay, so this one here has the minimum key, but it's the highest priority. Minimum key, but highest priority. Okay, symmetrically, you can think about right here. The maximum key is right here. Okay, you can think about here. This is the maximum key, but it's the lowest priority. Okay, so far so good. And also notice that the key value here do not necessarily have to be unique. It's okay to be duplicated, right? So let's say here we got 3 here, the key, and also we got 3 here as well. Okay, so let me put this down. So these are entries with the same priority. And in which case, does not really matter which one you choose. Which one to choose. Okay, and you may want to also consider compare. Okay, when we talk about like an entry, right? Okay, let me just put a comparison right away. So we talk about, for example, 2 kind of data structure. Okay, so data structure and also the row of key value, right? Let's start with, for example, search tree, like a binary search tree, versus, let's say, priority queue. Okay, of course, later on, we're going to see that it's going to be implemented by a heap. Okay. When we talk about binary search tree, we know that we have to go either left or right, each time on the recursion or iteratively. So the role of the key is actually going to be for uniquely identifying some entry. Uniquely identifying an entry. Okay, so unique here is the keyword, uniquely. Okay, cannot be any duplicate, otherwise your binary search may not work. On the other hand, for the priority queue or the heap, the keys over here only denote the priority values. They're not really for searching purpose. You don't normally search. Okay, you don't. So this one here, the keys may be duplicated. And they are not for searching. Not for searching purpose. Okay, so that's about priority queue. Yeah, that one just a quick reminder. Okay. Okay, let's now go back here. And then let me see if I miss anything here. Okay. And what about insert and remove? So these are the 2 operations we're going to see using a heap, right? They got similar running time, but the structure, the way they kind of perform will be a little bit different, but we'll talk about it. And when you say you remove, what does it really mean? When you say remove something from priority queue, it has a very special meaning. That simply means you want to remove the entry with the highest priority. That means to remove the entry with either you can say the lowest key or highest priority. You might see in other literature, maybe they talk about maximum heap priority queue. But in our context, since we're going to apply the priority queue in the Dijkstra algorithm, so we do the minimum key version. If I want you to consider like a maximum key priority queue, I will say that explicitly in the question. But just know that everything will be work kind of symmetrically if you want to do a maximum key priority queue as opposed to minimum key. All right, one more comparison. If you compare a priority queue with a normal FIVO, first in, first out queue, right? Let's now compare them very quickly, and then we can go on, talk about other things. So if you compare priority queue with first in, first out queue. Okay, right here. Okay. In priority queue, entries will be removed based on their priorities. So we say that entries in priority queue are removed according to the priority values. And for FIVO queue, it's kind of first in, first out, kind of based on the chronological order, like a timestamp. Imagine that you have some timestamp. Maybe the smaller the timestamp is, the earlier you're going to remove the queue, right? So entries in, first out queue removed according to the chronological order. Like a timing of insertions. Right, just compare these two queues very carefully, right? One is about priority values, the other one is about chronological order of insertion, right? So these are the two, right? So these are different, okay? You definitely cannot exactly use a FIVO queue for Dijkstra algorithm, simply not, right? Because inserting earlier in the queue doesn't really mean they got smaller capital D value, okay, intuitively. All right, okay, that's about the priority queue. And then let's now move on to, okay, the next part. And you will see different application for priority queue. It's actually very useful ADT to really think about. We're going to look at the common operation pretty soon. It can be just about the like a mileage. Maybe the more senior you are in some mileage program for some air company, maybe the higher priority you get. Right? There's a way to assign the priority key value. About network and also okay. I got another revised version, so this is another bullet point, right? So another way to really see the priority queue is the capital D value is a priority, which I just mentioned for Dijkstra algorithm. I'll update the slides. There's one more bullet point, which I didn't really have over here, okay? Okay, let's look at very quickly about the operations that you have to support for a priority queue. So the minimum, okay, so this one here, you just want to return the entry with the highest priority or the lowest key value. Just a minimum, okay? That one we'll see what the running time is. And also how many nodes you actually have in the priority queue, or how many vertices you have already currently in the priority queue. Remember there was a while condition there, so while the priority queue is not empty. This could be useful for the size, right? While the size is actually not equal to 0. And then you got it's empty, just a Boolean query, and also insert. You may actually, well, there are two basic operations. You want to insert some entry into the priority queue. You may also want to remove something from the priority queue. When you want to insert, the entry with certain key value and also some element value. So the key value here is very important. There are certain properties you want to make sure you actually maintain after the insertion, which we'll talk about. And notice that here, when we say remove, the operation is even more explicit. We don't remove an arbitrary entry from the priority queue. We remove the entry with the minimum key value or the highest priority. That's why we say remove min over here. So when you talk about maybe maximum key priority queue, you might say remove max accordingly. Okay. So these are the standard operations that will have to be supported by any data structure implementing priority queue. And now we're going to see one efficient operation, one efficient data structure called heap. Okay. All right, talk about heap. And heap basically is just a binary, like a special binary tree, not search tree. We don't really have any search property for the heap. So we're going to define what a heap is. Any binary tree that satisfies two properties can be called a heap. We're going to talk about these two properties one by one, okay, just to review. So a heap is a binary tree, which, again, is a collection of entries. We got key and we got value, all right? Somehow, the heap is going to make the entry with the minimum key very explicit for you so that you can easily extract it. But once you have extracted or removed the minimum entry, you have to somehow restore the tree back to the normal heap, just with one less entry. That's where the tricky thing comes in. We'll see. Okay. There's one example heap. We'll go over that in just one moment. So there's a takeaway for you, okay, very quickly. In order for a binary tree to be called a heap, you have to satisfy two properties. One is called structural property, the other one is called relational property. I'll talk about the structural property first, and then I'll talk about relational. Okay. Again, sorry about that. So this just happened to be the slightly outdated version of slide, but if you look at the website, maybe a little bit different. Okay. Let me talk about structural first. I think it makes more sense. To talk about the structural property, let's review some terminology for a binary tree. All right? So there is a notion about a binary tree being complete. All right? That might be something you have heard about back in 2101 maybe, but that's okay. Let's revisit that, right? Let's be fair, okay? It's been a while. So let's now go over what does it really mean for a binary tree to be complete. And then I can draw some comparison as well, okay? Let's take a look at this. A binary tree with certain heights, okay, I'll visualize it. It's a complete if, okay? So there are several conditions that must be satisfied in order for the tree to be complete. Let me go over bullet point first, and then we'll visualize exactly what's going on, okay? So number one, you have to go from level 0 all the way to level h-2. So we talk about a range of levels, okay? They should have exactly 2 children, maximum number of children, because we talk about binary tree. That's condition number 1. Condition number 2, for the next level, h-1, it's like a second last level. If you think about the bottom level, it's like an h. The second last is h-1, and then h-2, okay? That one there, we can have the freedom about either 0, 1, or 2 child nodes. And then the final condition is somehow the child nodes at the bottom level will have to be filled out from left to right. Okay, that's what we mean by complete. But let's visualize this. I would say when you study for this, what really means to be a complete binary tree, you want to maybe look at the visual example first before you look at the bullet points, right, to be precise. Okay, let's now go to, okay, for now you can just ignore just this part here, okay, just ignore. Let's talk about just this part here. What does it really mean for a binary tree to be complete? Let's go over that first. And I have a particular tree here. The height is 3. Why is that 3? You can think about this is the bottom level. And then you can see the maximum depth is 1, 2, and 3. That's why height is 3, right? So when we define the height, it's the maximum depth in the tree. Let's just remind ourselves. So this is the maximum depth. And the depth will be the number of edges you have to go to really go to the root of the tree, right? So in this case, 1, 2, and 3, maximum. Okay? And then let's now divide this particular tree into different levels, all right? So let me divide in this way. So we got here, this will be the level where the depth is exactly equal to 0. Because the root to go to itself is simply 0 edges, right? Also, you got right here, the depth is equal to 1. Both both of these nodes will take exactly one edge. So that's why the depth is 1. Okay? And then this one here, the depth is equal to 2. And right here, the depth is equal to 3. Okay? Just label them quickly. And then you can see that right here, the 3 here just correspond to the height value right here. All right, let's now go backwards to see where exactly we are using the h value, and then we can see how the definition will work. So think about, this is level h. So this is level h minus 1. This is level h minus 2. This is h minus 3. Right? Or if you like, that's also, so these are the level. Okay? Of course, if the tree is much higher, you might just go all the way, right? Back to the root. Let's now look at what the definition says. Okay? Let's go bullet point by bullet point to understand what's going on. Okay? Bullet point number 1. All the nodes with depth less than or equal to h minus 2 has 2 children. All right? In our case, this is h minus 2, h minus 3, all the things smaller than or equal to h minus 2, right? So basically, these 2 levels, every node here has 2 children. This node here, 2 children. This node here, 2 children. This node here, 2 children. So bullet point number 1, satisfied. All right? So here, so condition number 1. Okay? So here, I would say condition number 1. From level 0 all the way to, including to level h minus 2. Each node has the maximum number of children, which is 2. 2 child nodes. Okay, that's condition number 1. Okay, just right here. Okay, let's now look at bullet point number 2. Bullet point number 2 is saying just one level. For all the nodes at the depth or level h minus 1, the next level, has either 0, 1, or 2 child nodes. Okay, let's see if that's the case. Okay, so now you can see that right here. Right here. So this one here is going to be condition number 2. So each node has 0, 1, or 2 child nodes. So you can see here, these are the nodes. For example, this node here has 2 child nodes. This node here has 1 child node. And this node here has 0. This one also has 0. So 0, 1, or 2. Only this level. Okay? Okay, so that's the Boolean condition. That's condition number 2. Okay, in order to be a complete. Okay, final condition, which is about the last level. So the child nodes of those h minus 1 nodes, they have to be filled out from left to right. Okay. So you can think about right here, these nodes. So these are, so that's condition number 3. The child nodes of the nodes at level h minus 1, right? So the child nodes of these nodes, basically, filled from left to right. Okay, condition number 3. Right, that's how you can understand about the 3 conditions here. All of them must be right. If any one of them is violated, you cannot call that complete binary tree. Question before I move on? Go ahead. Left to right, okay, good question. Okay, let's say for example. So this node here has left and right child. So far we are fine, right? Left to right. And in order to be a complete, let me ask you this. So here, can J be a right child? No? How come? From left to right, okay, good. So here, if J happened to be a right child, for example, in that case, left child will be null. In that case, you're not really going from left to right. Exactly. I'll write it down, okay? Damn it, that's something I wanted to say. I'm glad actually you asked me that question. So J here must be a left child. Okay, in order for that to be complete. Good, okay. Let's now do a little bit more numerical analysis. Given the structure of your complete binary tree, let's now try to calculate the number of nodes. That could be the maximum or the minimum. Let's see, all right? And let's now consider this diagram over here. Okay, this one here. Let's say we have the height h, conceptually, this is h, okay? So that means this will be the bottom level that we have to fill out somehow, okay? So think about here. You can think about this is the bottom level that we got to fill out, okay? So just this part here is basically level h, all right? And let's go backwards. If this is level h, so we know that this part here, just above it, is level h minus 1. Level h minus 1. And from here, from the root all the way to right here. So that will be everything less than or equal to h minus 2. Right? So we'll just make the tree structure so that we can check the condition for being complete. All right? So based on what we know that this part here got to be completely filled out, basically, right? From 0 all the way to h minus 1. We got to be exactly the same. It's got to be always completely filled out, right? What would be the minimum case for the complete binary tree? How many nodes should we have in the bottom level? Can we have 0? How come? It's a fundamental question, guys. Okay, let me ask again, okay? And then I'll let Josh answer. Okay, my question goes like this. I'm basically asking about what will be the range of the number of nodes in a complete binary tree. Okay, so I'm asking, is it possible I simply have no node at level h? Is it possible? Josh.
I would say no, because then it's not like you have a tree that's of height h. It's like height h minus 1.
Exactly. That's exactly right. Okay. Remember, we kind of started with the visualization. We assume that your tree has a height h. That means there's got to be at least one node here that's going to have the maximum depth all the way to the root. If you don't have any node here, then this will be the tree. In that way, the height wouldn't be h. It would be h minus 1 instead. All right? Hopefully that makes sense. Okay, given this. So it sounds like what will be the minimum? Just one? Where should we put that one node? Can we put it anywhere? Where should we put it? The leftmost, right? So somehow you have to find the leftmost node on level h minus 1 and put a left child right here. Okay, so this one here should be the left child. Okay, that'll be the minimum. And the maximum should be we got the level h completely filled out. All right? And so that'll be just 1. Versus if we got level h completely filled out. How many nodes? It also sounds a little bit basic from 2101. You guys know? What will be the maximum number of nodes if I want to get to level h? There's a little formula. I'll see how you guys react to this. Maybe I can do a little bit of review, maybe on Wednesday as well, just to help you. Okay? But what is that? Just the bottom row. I'm not talking about whole tree, just the bottom node.
2 to the h, right?
2 to the h, yes, that's right. Okay, good. Okay, I'll try to give you guys maybe some background, maybe just one page. Take me 10 minutes to review. I can do that, okay? But for now, I'll just write it down for you. 2 to the h. Whenever you want to calculate what's the maximum number of nodes in a particular level, you just say 2 to the power of that level number. Okay, starting from 0 all the way to, the maximum. Okay. All right, so given this, we can now calculate for the whole tree that's actually complete. What will be the minimum and what will be the maximum? Conceptually, it goes like this. We know that for either the minimum case or maximum case, this part here must be complete. Right? This part must be completely full. And then minimum will be just add 1 to it. Maximum will be add 2 to the h to it. Right? So now, let's now calculate what's going on. So I'm going to do, let me just try to use a different color here. Think about just right here. This part here is going to be what's going to be shared between the two cases. Just this part here. Okay? Just this part. That one there is more like a geometrical sequence, which we did derive the formula back in. Remember when we talk about dynamic array, we're trying to derive the geometrical sequence. You may want to review that formula quickly. I'll remind you about the facts very soon. Okay? So for both of them, just for the blue part, it's going to be 2 to the 0 plus 2 to the 1 plus all the way to 2 to the h minus 1. And this part here as well. Okay, that's the one. And what should that be? Okay, I'll write it down over here. Let's say that's a star, right? If I got 2 to the 0 plus 2 to the 1 plus all the way to 2 to the h. Okay, I want to remind you very, very quickly. Okay. When we earlier spoke about, I think it was in the first, maybe second week or third week, you can double check. We did talk about it in class, but I'll write it down, okay? Whenever you got a geometrical sequence, okay, right here. So you got some sequence of k terms, okay? So this will be the number of terms. Number of terms. And then it's going to be, okay, the result is initial term multiply common factor to the power of the number of terms minus 1 r minus 1. Okay, I'll put some annotation here. So this is the first term. And the r here is a common factor. So this is a general formula, right, for any arbitrary first term, and also common factor, and also number of terms. But in our case, we only worry about binary tree, right? So the way we talk about it is more like this, right? Let's say this is your binary tree. You basically got the first one, and then this is level 0, level 1, etc. Right? You basically got 2 to the power of 0, 2 to the power 1, and etc. Right? That's kind of a particular sequence. So in the case of binary tree, so the first term here is just 1. Okay, I'll put it down. With h levels. With the heights being equal to just h. Okay, so we've talked about here, maybe all the way to the bottom here. So the level is simply just h, let's say. All right. In that way, we're just going to get, so the very first term will be simply 2 to the power 0, just 1. And then the common factor will be just 1, and then 2, and then 4, and then 8, right? Common factor is 2. And then we got 2 to the power of, so now how many terms do we have? we go from 0 all the way to h plus 1. Agree? Okay. H plus 1, and then minus 1, and then we got r minus 1. In that way, you just get 2 to the h plus 1 minus 1. All right, so review that geometric sequence formula, and then you can see how the formula can be derived. Okay, let's now go back to our case over here. Okay, so now we want to talk about this one here. Okay, this one here. Let me put the formula here. If you actually got for binary tree, if you got k terms, it's going to be 2 to the power of k minus 1. All right, this is about the number of terms. Okay, let's see. How many terms do we have over here? How many terms? From 0 all the way to h as the exponent. H terms? H plus 1, right? Okay, I assume you're okay with it. So it's going to be h. So it's going to be from 0 all the way to, oh, I beg your pardon, I make a mistake. I really apologize. Is we go from 0 all the way to h minus 1. Okay, that's the thing I got wrong. Okay, let me just fix that quickly. So this one here should be from 0 all the way to h minus 1. Okay, everything else was okay. Okay, so here we got 0 all the way to h minus 1. How many terms? H terms. Okay, so that means we're going to apply the k here will be h. 2 to the h, and then minus 1. Okay, so this number here is important to know how we kind of derive that. Okay, so we know that here, just this one here, just this part here is 2 to the h minus 1. Okay, in the minimum case, we actually got just one more node at the bottom level. And then that one's there, it's just going to be plus 1. And in the maximum case, it's going to be plus 2 to the h. Okay, that's how you derive about minimum and maximum. Okay, okay, this one here is just going to be 2 to the h. And this one here is going to be 2 to the h plus 1 minus 1. Yeah, the math should be right, but you can double check. Okay, these are the facts. Okay, that's about complete binary tree. So the way you study that would be try to visualize a simple tree like what I just provided. And then also try to look at the bullet points right here about what does it really mean for the tree to be complete. I would say this might be the trickier property to really get right for the heap, because for that to be complete, you have to know exactly how to understand it mathematically. Okay, good. And then also for your information, there is also a kind of tree called full binary tree. Full binary tree basically is a special case. It's basically a complete binary tree where at level h, at this particular level is the maximum. So that means we got everything right here. Okay, just everything. We have 2 to the h nodes. Okay, complete binary tree. Okay, let me just finish this and then we can take a short break. Okay, so that means for this one here, we're just going to get right here everything all the way to 2 to the h. Okay, so think about this one here. It's just going to be 2 to the 0, 2 to the 1, plus all the way to 2 to the h, which will be, you can see that we got 0 to h. So we got 2 to the, so how many terms? We got h plus term. h plus 1. Okay, and then minus 1. So that's according to the formula right here. How many terms do we have? We got h plus 1 term. Okay. All right. All right, questions about this? All good? Okay. This might be the trickiest one to really get right, but other than that, I think we just need to cover the relational property, and then we can see what a heap is. Why don't we take a very short break, and then we'll resume. All right, so before the break, we actually went through about a formal definition about why, what does it really mean for binary tree to be complete? All right, minimum, maximum. That's about the structural property. All right, so whenever we talk about a heap being structural, so that means the heap itself must be a complete binary tree. Let me just go here to show to you. Okay, that's property number 1. All right, so heaps. Okay, so when we talk about structural properties of the heap, it's a tree, a binary tree with a structural property. So this is a maximum number of nodes that we just learned from before the break, right? I'm just copying that over from the page, the maximum number, okay? So this will be the maximum number of nodes. And then we don't have to do that detailed process here, over here. If you rewrite it a little bit, you will see that n here, you will see that h here is big O of log n, okay? You can take this one for granted. You don't have to somehow derive this mathematically, even though you could. You just have to rearrange the terms a little bit, right? So given this, we know that h in the exponent, if you rewrite the term a little bit, h will be just big O of log n. So this one tells a very important property about the heights of the heap, okay? So now, if this is a heap, so very quickly you can see for this particular tree, so you have right here, and also you have right here, and also right here, right? You got different levels. So this is h minus 2, h minus 1, and that's h, right? If you check all the 3 bullet points, the condition, you will see that this one here satisfies the structural property, okay? So the most important thing is we should know that given that it satisfies the structural property, so that means the h is big O of log n. So this one is very important whenever we want to do any insertion or deletion. Is going to guarantee we got efficient, like a running time, as opposed to maybe linear, right? Remember we spoke very earlier back in the course when we talk about why you have to do tree rotation, which is another kind of a restoration mechanism for the high balance property. So here we want to make sure it will remain to be a complete binary tree. In that way, we can be guaranteed the height is always log n. Okay. So I'll put something here. You can compare the heights for self-balancing binary search trees. Okay, similar. We want to make sure the height is log n. Okay, the minimum height possible. Right, so that's about structure. Okay, so if your binary tree only satisfies the structural property, that's not sufficient. It's necessary, but it's not sufficient. So the other property that your binary tree must also satisfy is so-called relational property. Okay, so that one there, let me show to you. Okay, it's actually here. And the property is very easily defined. It's called a heap order property. It goes like this. You have to go to every child node other than the root, and then compare the key value. Compare the child node's key value and also the key value of its parents. It must be that, since we are assuming that we got a minimum key heap, right, like a minimum key priority queue, we want to make sure the key value for the child is larger than or equal to the key value for the parents. Okay, that's the property. But let's double check. Okay. For example, if you look at this one here, you can see 16 larger than or equal to 15. 15 larger than or equal to 5. 5 larger than or equal to 4. Just one example. All right. Let's now write down the different lemmas we can derive from the heap order property. Okay. And it's a reminder for every that this is a heap order property. The key value for the child is larger than or equal to the key value of that particular child node's parent. Okay, that's the definition. Okay, property number 1. For property number 1 here, any leaf to root path. For example, if you go from this leaf here all the way to the root, that's one path, right? This one here, another path, right? You talk about all the leaf to root paths. Generates a sorted sequence of keys. Let's see exactly what kind of order, okay? So for example, I'll just take one example here. So let's say we go from here, here, and then here, and also here. You can see we go 12, 9, 5, and 4. You might be thinking just decreasing. However, not necessarily strictly decreasing because we do allow duplicates of a key, right? So the most accurate of saying that will be non-ascending. Okay, I'll put it down first. Non-ascending order. As long as it's not increasing, we'll be okay, even though the key might be just the same. Okay? So basically from here, when you compare these two, as long as it is not the case that 12 is strictly larger than 9, it is not. Right? It's not ascending. Okay? Think it that way. Oh, beg your pardon, I said the wrong way. As long as it's not 12 less than 9. Because if 12 is less than 9, in that way we're actually ascending. Right? Ascending in this case, but we're not ascending. Okay? Non-ascending, that means the child key might be equal to the parent key. Or the child key could be strictly less than the parent key. Larger than. Yeah, just be careful about the sign. Right, you can see this case, 12 is strictly larger than 9, so we are fine. All right, so larger than or equal to, okay? Not ascending, good. That's property number 1, and property number 2, which is so important to see where the minimum is. The minimum key is stored in the root. Okay, so this root over here is the minimum key among all the entries, guaranteed. So let's say if you're using this heap here to store all the vertices where the key value is the capital D value. So now if I want to now choose the vertex for the current iteration, what should I choose? I choose the root, right? Easy. So extracting the minimum should be a very efficient operation, big of 1. You just take the root. All right. However, if you want to remove the minimum, that's going to cost more because you somehow want to do some replacement. We'll get there. Okay. All right. So property number 3. Oh, before I talk about it, I can also show you another thing. So this property number 2 here is more like a recursive kind of property, right? So if you think about the whole tree over here, then this root over here is the minimum key. However, if you look at any subtree, the same property will also apply. So what do I mean? So if you look at, for example, this particular subtree, right? This subtree here also should satisfy the relational property. So this subtree here, the root has also the minimum key value for this subtree. The root also has the minimum key value. Okay? All right, the final property. The keys between left subtree and the right subtree, they are not related by any connection. There's no property between them. Okay? There's no property we can say about between left subtree and right subtree. Are not related. So for example, if you look at the 15 over here and also the 9 here, you cannot say anything about it. They can be the same. They can be maybe one is larger than the other. Doesn't really matter. Okay? They're not supposed to be related. They are not related. Okay? Let me just use orange. If you use here and over here. Not related. The only thing you can say is guarantee 15 should be larger than or equal to its parents. 9 should also be larger than or equal to the parents. That's the only thing you can say. That's which is the heap order property. Okay, I'll write it down. The only properties is with respect to the parents. Right? So let me just say right here. Okay, let's say for this particular case, right? If you look at these two over here, so you can say that, for example, 15 is larger than or equal to 5, right here. And also here, you can say 9 is larger than or equal to 5 as well. That's all we can say. Just compare with their parents, but you cannot say anything about the siblings. Okay, that's a relational property for the heap. So now in order for a binary tree to be a heap, you must satisfy both the structural and also relational properties. Right? Questions? Good? Okay, let's now do some very simple exercises and then just to see if they are really heap. Okay? Is this a heap? It is the simplest one possible, actually. In which case, it's complete, well, only one level, right? Just level 0. And also, there's no parent to complete. Well, think about it, you cannot find any violation for the relational property or structural property, okay? So this is a one-noded heap. Just one single node, okay? And question, is this a heap? Is it complete, first of all? You can see here, and then from this level here, you go from left, so that's okay. And also 6, so you think about this is left, and also 6 is larger than or equal to 4. So it's a heap, okay? Good. I'm just checking both the relational and also the structural property. So this is both complete and also satisfy the heap order property. Okay, that's an acronym I will use. Heap order property. How about this one here? Is it a heap? It's not a min heap. Yeah, well, we talk about min heap, right? So it's got to be a min heap. Is it a min heap? No, right? So is it complete? Yeah. Is it complete? But it doesn't satisfy relational property, right? So this one here is complete, but violates the heap order property. All right, how about this one here? Is it a heap? No? Yes? Okay. Is it complete?
Oh, no.
Because yeah, it's not filled from left to right, right? So because at the bottom level, it should be from left to right, exactly. Okay, it's not complete, but 6 larger than equal to 4 is actually okay, right? Satisfy 1. Okay. So this one here is not complete, but satisfy the heap order property. Okay, you can just see different flavor, right? Just gotta be sure you satisfy both. All right, so these two, you can double check. So these are heaps. It will be complete and also satisfy heap order property. Okay. So these two example, you can just double check. So these are heaps. Okay, right here. Okay. So there are two more things I want to say about a heap, but we will not be able to do it today. So basically, we're going to talk about how you can do insertion and also how you can do deletion, right? Both are important because both operations will be used in the Dijkstra algorithm. That's something we want to be sure we know about, why the running time is the case. So I will start with these two examples from Wednesday. So we'll finish these two, and just to show you the example, and also you can see the pseudocode or like an algorithm, the steps on the slides. I'll mention them very briefly in the beginning. And after these two, we're going to go back to the Dijkstra algorithm, and then we're going to derive the running time. So it doesn't really hurt if you can just go to that particular slides. I'll show to you. Okay, and then we're done for today. You can take a look at slide number 66. If you look at that over here, can you already try to see if you can derive the running time to take a look? Of course, you can see the final outcome, but I would say not to really go there. If this is something I just gave to you, I may modify that a little bit. So the running time will be different, right? So if you take this one here, and then to see how the running time should be derived, okay? I can tell you that the tricky bit is really going to be to see how many iterations you have over here, and also how many iterations you're going to have over here. And then to see how this one here can be done, okay, right here. Okay. But I would say give a preview about what might be difficult for you. So when I derive them, I'll derive the running time Wednesday, it will make more sense. Okay. And so after the insertion, deletion of the heap, after the running time, I'll talk also very briefly about the final strategy for implementing a graph using a 2D array. Okay. After that, we're done for the coverage for test 2. Okay. So if I cannot really leave any time for you for Q&A for Wednesday, I can give you some extra office hour just for you to ask questions if needed. Otherwise, I'll see you on Friday. All right. Thank you. I'll see you on Wednesday.